Let's start with the lecture. Today we will discuss about the nucleus stability or the nuclear stability, and this is one of the first topic because you must understand either the nucleus is stable or it is unstable, and what are the factors actually making them unstable. And then further on we will move to the how to be differentiate the stability of the different nuclides. So first have the look on the atom. This is the atom, or it is the nucleus, and these the extra nuclear parts. That mean only the electrons are there. So here our concern is the to discuss the stability of the nucleus only. Not we are here, we are not considering the extra nuclear part, that means the electrons. So if you have a look at the nucleus, so nucleus is having the number of the protons with the positive charge and the number of the number of the neutron with any charge over there. These are the neutral particles. So these are the having the positive charge. These are the protons. So this is another example. Let's suppose this is the helium, and this may be the lithium with the 2 protons and with the 3 protons. So if you look at the helium atom or the lithium atom, and similar to the other atoms or the nuclides, all the nucleus having the overall charge is the positive. So the question over here is, if the charge with the nucleus is positive and the neutrons are having a neutral charge, then there should be repulsion between the positive and the positive charge. Let's suppose these are the 3 protons. They must repel to each other, and then this nucleus must be a unstable nucleus. That means they should not be allowed to bind themselves within the nucleus, and this is the main question, and the answer would be in this lecture. Actually, this is we are going to consider the nuclear stability. So let if I so these actually the protons having the positive charge, they are within the nucleus. Of course, there should be some energy, or you can say this is maybe the binding energy or the forces which are going to be existed within the nucleus, which are binding the nucleons. Nucleon means the protons as well as the neutrons inside the nucleus. So let's have a look another picture over here. This is the same helium, and helium is it is in this nucleus and the extra nuclear part. Again, we are only concerned with the number of the protons and the neutrons, and we call them the nucleons. So here, this is the actually I am weighing the helium nucleus because having this one unified mass 4.00150, and this helium is composed of with the 2 protons and the neutrons. That means this must be a helium, and the mass of over here is the 4.03188 unified atomic mass. And but here you can see there is a difference in the mass, and as uh, if this helium is composed by the joining of the 2 protons and the 2 neutrons, there should not be any the difference in the weight, but there is the difference is the weight. And the weight you have a look over here, the mass of 2 protons and the 2 neutrons must be equal to the mass of the helium. but here individually mass of the two protons or the neutrons is more as compared to the mass of the helium nucleus. Again, I am just talking the nucleus. So there is the variation in the mass. So what is the this mass actually giving you the idea? That means there is the mass of the sum of the protons and the neutron is more as compared to the mass of the helium nucleus. And this is the difference in mass, and this difference in mass is called the mass defect. That means the mass is missing. Where it is missing? It is missing in within nucleus, helium nucleus, because it should be equal to the mass of the two protons and the neutron, but it is less. That means some mass is missing, and that mass is called the mass defect. Okay, where it is going, that means it is converted into the energy with the Einstein, the equation E equal to mc square, and you can convert the mass into the energy. And in the previous lecture, we have actually defined and calculated the conversion factor, which was the 931.5. So if you multiply that factor with the mass, that mass is converted into the energy, and this is called the binding energy. Actually, this energy, the mass cannot be lost in case, because it is just missing here, and where it is converted into the energy, and that energy is called the binding energy, actually, which are binding the nucleons within the nucleus. So this is called the binding energy. The reason is uh, what type the forces are there. Actually, this is the binding energy which is binding the nucleons, nucleon being the protons and the neutrons within the nucleus, and that is called the binding energy. And where it is coming from, this is coming from the loss or the missing mass, and we call it the mass defect, which is this is the actual mass and this is the calculated mass. And you can easily calculate, this is the this minus this, that means the calculated mass minus the actual mass. If you minus them, these two masses, then you can get the mass defect. So here I am further explaining, and important over here is in nuclear chemistry, you can calculate the binding energy by a very simple way, and this will be the methodology we are going to use in the coming lectures. So you must understand how to calculate this one, because this will remain the same. Again, throughout the lecture, we are playing with the number of the protons and the neutrons, and we are concluding a lot of the ideas out of the playing with the number of the protons and the neutrons. So that's why I'm taking with the very basic information. Again, the binding energy, this is the carbon 13, and carbon 13 is having the atomic number 6 and mass number 13. That means 6 proton and 13 minus 6, they are the 7 neutrons. So they are written over here. It is composed of with the 6 protons and the 7 neutrons. And if the mass of the sum of the mass of the 7 protons and this sorry 6 proton and the 7 neutron is equal to the actual mass of the carbon 613, then there is no difference in the mass and there is no binding energy over there. So actually this is more as compared to the this. So that's why, to balance this one, as we balance the nuclear reaction, the total mass and energy at this side must be equal to the total mass and energy this side. So right hand side must be balanced with the left hand side. So the only difference here, there is the some extra mass is going to exist over here, and that is converted into energy. And if the sum of these two, that must be equal to each other. So our concern is this nuclide is having less mass as compared to the sum of the masses of the protons and the neutrons, and it is converted into the energy that is called the binding energy. And these are the values are given over here. The mass of the protons is this, mass of the neutron is this in the unified mass. And this is the equation we have used in the previous class. Again, there is no need to change to use all the conversion factor, and we will just use this conversion factor. One unified mass or one atomic mass unit will be equal to 931.5 mega electron volt to convert the mass into the energy. But here again, it is also, this is the BE is the binding energy as we have explained. Again, how can you calculate the binding energy? And inside this is the mass defect, mass of the neutron plus mass of the proton minus mass of the nuclide. This is the mass defect. When you multiply by the c square, this is the actually E square mc square. This will give the energy. Again, I'm explaining. We will just calculate the mass defect and multiply by this factor. That will give you directly the energy in mega electron volt. So let's move to first to calculate, and then we will do some sort of the exercise over here to calculate the mass defect and the binding energy. Again, let's example is the helium. Helium atomic number is 2, mass number is 4, and having the 2 neutrons and the 2 protons, and plus it is releasing the binding energy. And now you have to calculate how much binding energy it is going to release. And not only it is important to know how to calculate the binding energy, and later on we will compare all these type the different binding energy of the nuclides, and we can compare the stability of one nuclide with the stability of the other nuclides, because in nuclear chemistry the stability is important, and you can suggest which one nuclide is the radioactive and which one is not radioactive. And if it is a radioactive, then what type of the radiation that specific nuclide is going to emit. And this will we will also decide in the coming lecture. So how to calculate? The first is the combined mass of the two hydrogen atoms and the neutrons. Hydrogen atom means the proton. We are talking with the protons. So these are the two protons, two neutrons, and the mass of one neutron is this. As it is the standard, you must remember this value. If it is not given to you, at least there are the only the few values you have to remember. Otherwise, everything will be given to you. So there are two neutrons. You have to multiply one this one. This will be the mass of two neutrons. In a similar way, you can calculate the mass of the protons. This is the mass of one proton, and you have to multiply by two. This is the mass of the two protons, and this is the sum of the mass of the protons and the neutron. That means 4.0328081 to unified mass. Now this is called the mass defect. Sorry, this is the mass of the protons and the neutrons. And now we are going to calculate the mass defect first. And the actual mass of the helium nucleus is the 4.00261. And remember here, and this is the calculated mass. Calculated mass must always be greater than the actual mass if the nuclides are stable. So this is the actual mass. And how can you calculate the mass defect? Simply calculated mass minus the actual mass. So this was the your calculated mass, and this is your actual mass, and you can say the difference in mass is 0.03038 u, and this is called the mass defect. That means the missing mass in the helium nucleus. And now you can convert into the energy, and simply what you are going to do over here, this is the factor 1 u is equal to 931.5, and you are going to multiply with this with the 931.5. So this is, sorry, the 931.5. I'm going to correct this one. Just wait. Okay. So this is the 931.5, and you multiply this will give you the value of 28.3 mega electron volt, and this is the binding energy. It is the this is the mass defect, and this is the binding energy. Actually, this binding energy is the energy which actually bind the nucleons, these two neutron and the protons within the nucleus. That's why these are even having the positive charges, they are stable in the nucleus due to this binding energy. Now, another important point over here is to calculate the average binding energy. So why does it need the average binding energy? Because now we are going to compare the binding energy of one nuclide with the binding energy of the other nuclide. So just as a common practice, if you move from hydrogen till the, let's suppose the uranium, the number of protons and neutrons are increasing. However, if you calculate the binding energy, the binding energy will also increase from hydrogen till the uranium or so on, whatever. That means the atomic number is increasing, so number of protons and neutrons are increasing. So the difference in atomic number and the the actual and the calculated mass will be increasing. So the binding energy is going to increase from hydrogen till the uranium. I am taking the example of the uranium because you know uranium is the radioactive element. So if the binding energy of the uranium is more than the binding energy of the, let's suppose, the carbon 612 or the helium 24, then it must be more stable as compared to the carbon or the helium. That means uranium must be more stable as compared to the carbon and the helium. But this is not the case. So that means we need some other parameter to differentiate between the stability of the different nuclides. So uranium must be more unstable as compared to the carbon 6 12 or the helium 24. So what is the reason behind this one? Now we are going to consider the average binding energy. So average binding energy is very simple. You are going to just divide with the number of the nucleons. So binding energy per nucleons, it is called the average binding energy. That means it will give you now the binding energy of a nucleon. That means the protons and the neutron. So in other way, you can say this is the mass number. Nucleon, the sum of the protons and the neutron is it is the mass number. So, but here in nuclear chemistry, it is the better term to be used. It is the binding energy per nucleon, and this is called the average binding energy. So let's see. Again, this is the same equation I am just using because this is the proper way to explain. Again, inside this is the mass defect, and when you multiply by c squared, this is would be the binding energy. And when you are going to divide with the nucleons, and here these are the nucleons or the mass number, then it is called the average binding energy. And how can you calculate? Simple. We have already calculated the binding energy of the helium, and the number of nucleons are there are four because two neutron and the two protons. So here are the four nucleon in this case, and you are just dividing by four, and this will give you the average binding energy, and you can say average binding energy per nucleon. So this is all about our today lecture. So here you have learned first, the objective is to understand the stability of these nucleons within the nucleus, and we have concluded with the reason there is some sort of the binding energy inside the nucleus, and this is coming out from the mass defect, and this is required to bind the nucleons within the nucleus. So then we move to the average binding energy, and I have already given the reason. When you compare the stability of one nuclide to the other nuclides, then you must need the average binding energy. Now you can compare which one is having a more average binding energy, that is the it would be more stable as compared to the other nuclides. So this is the proper term which we can use in comparison of the different nuclides. So before ending this one, I am just taking another exercise, and I suggest you must calculate this one, and then we will discuss the result later on.